calories per mole nitrogen times Kelvin.
Quick question.
Yeah.
I'm just asking because, like, for the stoichiometric coefficients, it's moles in H3 per mole N2. When you're using the coefficient for N2, though, would that be moles of N2 per moles of N2?
Yep.
So,
Which cancels out,
oh,
which is fine because the heat capacity also is in per moles of N2.
Okay, yeah, because you want it in moles of N2.
Right, right. And you don't have to do it that way, but almost always you're going to do it sort of as written, so to speak. So you're going to use those stoichiometric coefficients in that way. And that's because that's how we define conversion, right? That's how we define everything else. So it would be very silly to have a different basis for delta heat capacity or delta reaction, delta H reaction versus conversion. Okay, so going back to the original equation, right? Delta H of reaction at some temperature. But now I can replace that term with this one to make my life a lot easier. And if I substitute in for everything that we have, we get a value of negative 97. He switches units, don't ask me why. 97,530 now joules per mole of nitrogen. Or more commonly, you would see this written as 97.53 kilojoules per mole. Yeah?
What is T reference?
In this case, it's wherever you got your heat of formation energies, but that's almost always going to be room temp, 298. So yeah, the reference is just whatever you use right here. And just to give a second example, so this is delta H reaction at 423 Kelvin. Right, same temperature. But you can also define it as right? Everybody see that relationship? So it's just a factor of 3 difference, and that comes from the stoichiometric factor for hydrogen inside this formula. So these moles nitrogen, are they the moles flowed into the reactor? No, what are they? Moles reacted, yeah. So if you really, really want to be verbose in your units, and that's why this stoichiometric factors is what relates to 2, right? Because for every 1 mole of nitrogen I react, I'm reacting 3 moles of hydrogen. The amount of heat released is the same, so that way the heat of reaction has to be adjusted because this would be multiplied by a value 3 times larger.
So just checking, the temperature's only effect was on the given CP values. The CP values were just for at that temperature?
Yeah.
And that's like...
Well, not at the temperature. Remember that you were given these average values. So the average values were evaluated between the reference temperature of 298 and the reaction temperature of 423. But the heat capacities themselves can change as a function of temperature based on like an empirical model like that. And you can integrate this empirical model, right? So you can find these values, not those, but we erase them. Right, if you're asked. You know how to look, you know how to calculate those. If you were given those stoichiometric, that relationship, and you knew where to find those constants, alpha, beta, and gamma. All right, just 1 minute. Mixed up the notes in like 5 minutes today, so that's good. All right, we're going to continue this example. Now we'll actually talk about a reaction rather than just calculating something that you calculated in general chemistry. So let's calculate the delta T versus conversion for ammonia synthesis adiabatic flow reactor. So did everybody remember what adiabatic means? Well, consider this review if you don't remember. So let's first just write out the energy balance. It's a flow reactor, so what is delta E with respect to temperature? 0. We assume that we're at steady state within our flow units. And on this side, we have Q dot minus the shaft work. So some of this is review from last time. I'm just skipping ahead a little bit compared to the energy balance that we wrote down to start the class. So again, I know that we didn't write that energy balance today, but we did last time we talked about this.
There was a derivation.
Yeah. Yes, there was a long derivation for this. So adiabatic means what? Within this formula.
Q dot.
So adiabatic just means that we're not transferring heat into or out of the system. You're going to see a lot of problems that say adiabatic when we're starting to work on these. We're going to have a lot more problems where I'm going to ask you to operate a reactor isothermally. You're going to have to tell me how we're going to do it. How much heat do we have to remove? What type of, flow rate do we need on some cooling jacket? That type of thing. But we'll get to that later. Okay, so Q equals 0. What about shaft work? I just said adiabatic flow reactor. I didn't say what kind. What do we do with that? If it's a CSTR, then there is an impeller. If it's a PFR, there's not. So do we just assume it's a PFR? Yeah. No. We could leave it in, but does an impeller provide a lot of energy to a system compared to a reaction? So even when there is an impeller, you're often going to treat that shaft work as 0. Especially if you're not given any information on what the shaft work is. You're probably not going to calculate shaft work from first principles, so you're just going to assume that it's essentially 0. So some other things, we're going to have a stoichiometric feed. So what is theta B? If we have A, B, C. So what's theta B? Theta B is equal to C. 3. Yes. 3. Stoichiometric feed, right? And so theta C is equal to what? 0. And we'll also just say, for the point of clarity, that we don't have any inerts within the system. Okay, last piece of given information, the initial temperature going into the reactor.
Why is theta C?
Why is what? If it's a stoichiometric feed, that means you're not feeding any product. And so the initial temperature going into the reactor is 100 Celsius. what you get after you simplify things, and I'll show you where this came from in just a second. Okay, so if both of these are 0, we have a flow rate in both terms, so the flow rate just drops out. I'm substituting in over there the thetas, so you get 1 times the heat capacity of A, 3 times the heat capacity of B. C doesn't show up because its theta is equal to 0. And then we have this term is pretty much unchanged on the left.
Is that CPA average and CPB average? Or, because you have hat on that side, but you don't have hat on that side.
Yeah, it should be because we don't have an integral, so that's just missing from the notes. Yeah, I don't know why he lost his hat. And what is our reference temp? 298 Kelvin. And then this one is 373 Kelvin. Don't confuse T0 with TR or TREF, right? They're totally different. Okay.
T0 is the initial temperature going into the reactor?
Yes.
Okay.
T0 is like FA0, right? It's the inlet. T reference is whatever you use to get this value. That's your reference temperature, which is almost always going to be 298. Okay, so rearranging some more. Because again, we want to solve for temperature. So we'll collect those terms. CPA